thank you all for coming. This, as you're aware, this is the Master's Defense of Leo Araujo, who's a Brazilian Navy officer, who's been with us for 2 years and has to finish in 2 and a little bit years. And we're very lucky he's going to be able to present to us, admittedly remotely, but his thesis presentation. So I think the best thing would be just to give everyone an idea where we're allowing, there's some discussion on the time, but so generally 40 minutes for the presentation. If you go shorter, I think people don't mind. And then there will be discussions starting with the committee first, and then we'll be opening it up to the full group of participants. But rather than waste people's time, I'll allow Leo, if you'd care to start.
Starting my time here. Good afternoon, everyone. I'm Leo, and today I would like to share with you a little bit of the work that I developed during my time at CCOM. Before proceeding, I would like to thank the presence of you all, especially my committee members. Without them, this thesis defense would not be possible today. Thanks for all the efforts, John, Brian, and Tom. The goal of my thesis is to show that phase data can provide us with extra bottom detection information if we use it in a different way than we are used to. And as bottom detection, I mean bottom and any other submerged target. Today I have 2 friends here with me. They call Panic and Calls, and they are trying to mess up this presentation. So if something goes wrong, totally not my fault. Throughout this presentation, I plan to use these topics to remember the methods we use nowadays, share my ideas, results, and conclusions, and then indicating where it's possible to improve. As said by John, I work for the Brazilian Navy at the Directorate of Hydrography and Navigation, DHN, which is similar to NOAA. We produce nautical charts, and we need to perform hydrographic surveys. They have some resolution requirements, and it's related to the bottom detection algorithmic performance. A sounding can be defined as a time angle pair. And to obtain these pairs, we can start with a direction, picking a beam, and go through its time series to get a detection time. Through the time series and get a detection time. This is the classical conventional method. The second way is very similar, but we start with a time across all beams, I call it a time slice, to get a direction, or as many directions as possible, and complete the pairs. So we can work in time series within a beam or time slice. Now that we know this difference, let's see how we can apply them to our amplitude and phase data, starting with the amplitude one. With this data, time slice, time series, amplitude detection and BDI can be performed, and in both cases, a threshold must be defined, and echo envelopes are used. The first case, amplitude detection, consists of, for each beam, I have one beam here, a detection instant within an envelope where the highest amplitude occur is sought. So I need to find a time here. In BDI, within these echo envelopes, I'm looking for a direction. So let's remember how BDI works. To use BDI, we need overlapping between neighboring beams, allowing that a scattering point on the seabed to be received in several main lobes of beams. This scattering point is considered to be close. The result from here is like this here. and this scattering point is considered to be close to the beam where we have the highest intensity. Note, however, it should not be considered exactly at its maximum response axis. This is my maximum response axis for the green beam, and my point is here, not exactly the same. The correct direction is somewhere between my beam green and my beam red, somewhere around here. Parabola fitting seems a practical approach as it reasonably mimics the main lobe of a typical beam, and the abscissa of the parabola's peak is used to estimate the scattering point direction. It's also necessary that geometric corrections are made and that the data have corrected TVG so that the information of each beam can be compared. As people from CCOM knows, amplitude detection made in time series has better performance in near normal incidence, and in the BDI, the echo envelopes are better defined when the signal comes from oblique incidence. So they have complementary solutions, amplitude and BDI. After the amplitude data, the second piece of information that we have is the phase data. On left, we have the amplitude, here just a seabed with a small slope, and on the bottom, a shipwreck. And on the right, I have the phase data of this boat here. Note how it looks random the most of time, but near a target, remember, I see that here, near the target, the phase kind of looks like a rainbow, has a rainbow-like behavior. Also, I can see the shipwreck here. I swear I'm not trying to do a color blindness test now, but after a long time looking at these images, I realized that the direction in which we look at this rainbow can be important. But first, let's remember what is this data. Phase data is obtained by splitting an array in two subarrays, steering them to the same location, and measuring the difference between the phase information on each part. As the wavefronts interact with the seabed, the phase information starts to form a phase ramp. And the sign of the phase, positive, negative, or null, may indicate a direction relative to the border site. The null value, or zero crossing, indicates the moment when the signal came from the beam's border side. Phase detection uses the same envelope defined by amplitude detection. And as you may remember, they have a better performance in oblique incidence. Oblique is this case, and a normal one. Performance is better here. Note that this is the same situation than BDI. So as a result, the manufacturer seems to have left BDI aside, using only time series in their bottom detection algorithms. As the wavefront interact with a target before and after the MRA, so the maximum response axis, have interaction before and after, we can use other than zero cross phase information to provide more solutions within the same phase ramp. It's called the high density beamforming. As the manufacturer knows the relationship between phase difference and the mechanical angle of the receiver, phase values can be converted into angles with respect to the border side. I know the figure is small, but it's not important the format, just the idea. And fractions of the same phase ramp are used, resulting in new time angles pairs. So here is my phase ramp, classical zero crossing, but I can use more information from this phase and generate three solutions within the same footprint using the same phase range. This is the high density. And another feature, the last one to remember, all we have is called multiple or extra detection. It uses other echo envelopes to get more solutions. In this figure, I have one being here. Note it touch the top of the mast and then it find the seabed. So this echo envelope can get us the information about the seabed, and the second highest echo envelope that I can use will give me the information of the top of the mast. This is my extra detection. Now that we have seen everything we have, let's think about what would be an ideal bottom detection algorithm. It should be able to detect the seafloor and other targets from a minimal acceptable dimension, regardless of either it is on a vertical, horizontal, or oblique position, and regardless of its aspect ratio, being higher than wider or wider than higher. The question is, do we have an ideal one? Let's see one problem. In this example, we have water column amplitude data collected from a shipwreck. 45 consecutive pings are displayed. In red, we have the rejected or interpolated solutions. In light blue, the conventional amplitude and phase solutions, including high density beamforming. Note, all hair solutions, blue points, are found within my yellow ellipses. Almost never seen blue points within these ellipses. And these ellipses indicates the top of the mast, here, the top of mast, and the lateral extension of a shipwreck. So what is it? Is it a bottom detection problem? Let's focus on the lateral extension of this shipwreck. I have here the water column data, both amplitude and phase. The phase data is represented by colors, and a zero crossing corresponds to the color yellow, changing from red to blue or vice versa. Let's zoom in at this highlighted area here. And let's check all combinations of amplitude and phase times series times slice to see what's happening in this piece of information. So with using time series, it's hard to define in this amplitude information echo envelope. It's tricky because they kind of share the same intensity. They are pretty similar. And I cannot see in the phase information a phase ramp. It's hard to get a zero crossing because there is no classical phase ramp, so I can find or interpolate something and find a place. It looks like the entire time series is around zero. So let's try now with time slice. BDI and its parabola fitting should work. I can see here, it's the amplitude, the maximum amplitude, close to the beam number 92, so somewhere around here. But the problem is I need to think about how many points should I use to adjust a parabola, where should I put it? It's still tricky, but looks like it should work. And now the last combination, time slice and phases. I can see a phase ramp and a zero crossing somewhere around being 91 and 92. So it's pretty clear to see in this time what is the direction when I have a zero crossing. So what just happened? Let me try to explain. Again, phase data represented by colors. Null values are represented by the yellow color. The white arrow represents the conventional methods time series, and the orange arrow represents time slice. Many parts of the swath behave similarly to this figure on the left. In this case, using a time series, it's possible to obtain an instant corresponding to the zero crossing. So this is my time series. I know it's around this time here, I have my yellow, so I have a zero crossing. Likewise, when using a time slice, it's also possible to obtain a direction corresponding to the zero crossing. So here, found the yellow, okay, this direction here. Both methods are feasible, and time series has an advantage due to its data density. The situation of the central figure generally occurs around the nadir. The use of time slice in this case is compromised. Look that I'm traveling around the yellow all the time. I don't know each direction I get the yellow for the first time. I don't know here. So it's hard to know the angle to be considered. But using time series, it remains easy. You are able to realize in time series which time I can reach the yellow color, So the problem of this case becomes the duration. The transition between the colors can be so fast, which means a phase ramp is not long enough, having a slope close to the vertical line, that the definition of zero cross can be compromised. But a time series is, again, the better solution. Now, on the figure, this figure on the right shows a situation where the performance of time series is compromised. So if I use this time series here, I cannot find which time I'm crossing the yellow because I'm traveling around the yellow all the time. This is exactly the case that I show in the former slide. You are traveling around the yellow all the time, so it's hard to see a zero crossing, see a phase ramp. On the other hand, time slice can clearly define the angle which the yellow zero cross occurs. So I can find this angle using this time here. So what's your point, Leo? Sometimes the direction in which we look at a piece of information can be important. Vertical and horizontal direction can give us different results. It's beneficial to use both time series and time slice depending on the insonification geometry. So time slice seems to be useful. BDI has already used the amplitude data. Let me try use the phase data. I have a time slice here. This is all the data correspond to this time slice. And I can see phase ramps. But more than this zero cross in my phase ramp seems to be associated or have some relation with a peak here. When I put them both together, I can see a zero crossing and the peak. So, okay, that's officially my project. And my research questions are, can phase data improve bottom detection using time slice? And how the results behave when compared to conventional methods? My objectives are create an algorithm, test it in different areas, and compare the results. And you can think, and we can think, what's the meaning of this phase information across beams? Because we know the phase only exists within a beam. How can I compare using two different beams? Let's consider two neighboring beams, this red and blue, at a given moment, so at some instant. My star here represents the point of interaction between a wavefront and the seabed. Remember, the phase can indicate the angle with respect to the maximum response axis. So For my red beam, I know that this positive information for this time means that my star, my scattering point, is on its right. And for my blue beam, this time my star is a negative information, and it's telling me that my scattering point is on the left of my body side. If I could have a green beam whose maximum response axis was exactly at this star, at this scattering point, this phase would be null. I would be exactly here. So this is the complete view. At any time slice, if I get a time slice here, a scattering point will always be between two beams, two maximum response axes. And these neighboring beams, we always have a positive and a negative phase information for this time slice. So the task becomes how to discover under which direction the phase would be null. After making some assumptions and approximations, I believe that this value can be obtained by a straight line after correct the phase information, the phase value, with the steering angle with respect to the transducer. I'm not crossing a straight line from phase information to other. I correct them with the steering angle and then make this. The formula, the equation would took me a bunch of time, so it's just the hopefully idea of this my zero crossing. And now, before proceeding to my algorithm, I need to make some comments about thresholds. When we use time series, it's very likely that each beam will find a target at some time. And this will be associated with the high amplitudes in this time series. So a peak relative threshold can be used to define echo envelopes. For example, 10 dB from maximum. Just need to find which one is the maximum one, go down 10 dB, and this can define my echo envelope. The same here. So no matter which beam, a peak relative threshold can be used. But this does not happen with time slice. The use of a peak relative threshold can insert data that should be rejected or prevent the detection of data that should be accepted. For example, I have this time slice here in the water column. I should found nothing, but I have one peak, and 10 dB below the end would be give me this point as a solution. The same thing here. I'm reaching the seabed at two different points. So I have these two peaks here, but using 10 dB from the maximum would give me just this echo envelope because this one is below it. What I need to say is, using time slice, we need different threshold values for each time slice. In other words, an automatic threshold needs to be used. And luckily for me, a previous student tried to generate an automatic threshold to be applied in BDI. For each time slice, it was defined the maximum peak, minimum peak, mean of all peaks, a mean of range, a 10% range limit window centered on the mean range, and the mean all compared with these limits, the yellow here, can be outside or within these limits. When it's outside the limits, some peaks, this is my first case, some peaks are considered to stand out. So a cutoff value from the maximum is defined, and all data below this cutoff are rejected. So in this time slice, I'm just considering this piece here. The other case is when my mean of all peaks is within the limits, which is the mean range. I assume that all peaks are pretty similar, with no peak that stands out. So this is the case here, just the water column. In this case, the automatic threshold is set to a high value and the entire time slice is rejected. So I'm doing this automatic threshold for each time slice and defining a reference value to select my echo envelopes. This is a very good solution, but still not perfect, having many spikes. So to reduce the amount of spikes, a filter, I call initial filter, manual filter, is applied to the entire swath, and it rejects all elements with amplitude less than the reference value. So here is the complete swath, and here I'm rejecting everything below 30 dB, negative 30 dB. It's just a way to filter my initial data to perform my automatic threshold. Why do I need this? This is a result from this same image. So this is water column data, amplitude water column data, and my solutions. Using only the automatic threshold, I get this bunch of spikes here and here. And when I apply my initial filter, gradually it's going to reducing the number of spikes. So the challenge becomes to find a value that displays the smallest possible number of spikes without removing real data. Now that we have all the concepts, let's look at the algorithm and then the results. Initially, the amplitude and phase data are loaded. Then, a logical matrix containing the same number of elements as the water column data is created. All data set to false. Then, the initial threshold filter is applied to the entire swath. All elements above this reference value, the red curve here, all elements above receive the logical value of true. So I'm not going to check the entire time slice, just looking for these pieces here. And after my initial threshold, I'm going to apply my automatic threshold. Then each time is analyzed, all elements below this green value here, my automatic threshold, receive the logical value false again. This completes my envelope selection. So after all these steps, I'm just looking for these two pieces here. And using this filtering data, I'm performing that zero crossing in the phase information to find a direction, to estimate a direction. And as I have a time, now I have an angle, I can complete my time angle pair. It's kind of a BDI, but using the phase to perform, to get the direction. So a practical name that was we start to use is the PDI, P from phase. The data used were collected, surveyed, carried out in British Columbia, Western Canada, in 4 locations. Squamish River, where's the river, Leo? It's a picture from low tide, an area with steep faced dunes in very shallow waters. The second one is in the vicinity of Patricia Bay, where we have a series of concrete cubes. The other, a shipwreck of GB Church and the Mackenzie shipwreck. The echo sonder used was the EM24. It's operated at frequency of 200, 300, and 400 kilohertz and has the ability to save both amplitude and phase data of the water column. Now we get to the results. I have 8 examples to show, starting with the Squamish dunes. And I put this image here just to make sure everyone is believing me that I have dunes here. So let's first try to understand what's going to happen. I have here a time slice, and I can see 3 peaks. Each one of them is related with these 3 stars. Let's take a time series of the beam that contains this star on the right. Here is the time series. Note that the highest amplitude value is not the one that has a well-designed phase ramp. This makes the bottom detection algorithm for time series choose the wrong echo envelope. It's picking around here and not around here. So let's see the results. Water column data, amplitude information. Here is phase detection solutions and amplitude detection solutions. Note that we have a discontinuity here, and it's followed by wrong tracking of the seabed. The seabed should be around here, but we are tracking the wrong place. In my PDI, despite of making the same mistakes, despite of also tracking this smooth path here, I managed to capture the true seabed because I'm doing my selection time by time. So, and I don't have a number of limits of number of solution per time slice. So this time I get all these, and then I get 2 solutions, no matter the number. So looks like I can represent better in this case. This second example, we have a 0.5 meter side concrete cube with a pole of 1 meter length at 20 meter depth. Sorry, I need to drink. The amplitude and phase data are shown here in the top, and these 3 are the solution. Note KM means Kongsberg Maritime, the manufacturer from the EcoSonic that I use. Note that the solutions focus on the bottom and ignore the pole. With the feature of extra detection, a paid feature of extra detection, we kind of can think that we have something around here. Okay, maybe we are tracking the pole, but the shape does not correspond to reality. And PDI solution adequately represent the pole and the cube. But Leo, what's going on with this extra detection? Let's see. Using consecutive time slice, I'm able to see the pole in consecutive time, so I can get all the length of the pole. But using only a time series, this is the information, we can get within the same beam, the pole and then the cube and then the seabed, and detecting them becomes a problem to define echo envelopes. The best representation becomes just being the top of the pole, the top of the cube, and the seabed. It's really hard to create echo envelopes around here. But the problem is the main lobe of an adjacent beam. So I have one beam here. It's not touching, look here, it's not touching the cube. The main lobe is not touching, but each side lobe can feel this cube here. So if I attempt to use, if I attempt to use extra detection feature here, I'm going to get the seabed, but the next echo envelope will be here, and this is just a side lobe. So returning for the complete case, all you have here is a bunch of side lobe detections. Third example, here we have a 1 meter side concrete cube, again with a pole 1 meter, this time at 4 meter depth. And the performance of PDI remains adequate. The pole is ignored in the other 2. And we can see the extra detection is just completing the seabed here this time. Very similar to the former one. Example number 4. Again, 1 meter side cube, this time no pole, 20 meter depth. And this time at many incident angles. There are different lines. The first two cases are pretty similar to the previous one, with good definition of the cube and spikes by side lobes in extra detection. And from an angle of 45 degrees up to 70 degrees, the feature of extra detection almost doing nothing. KM solutions now contains gaps, and PDI become to represent an arc shape in the region of these gaps. So basically, we all are doing not good here, but this phenomenon of the arc shape here has already been presented in other works and is attributed to multipath. It's believed that the emitted pulse undergoes two reflections on two surfaces and return to receiver, resulting in a false two-way travel time information. In a way, the existence of these arcs of solutions can be used as an indicator of the presence of an object, and a new survey line under a more favorable angle of incident can be collected to better define this target. Example number 5, lifeboat davits at GB Church shipwreck. In this case, these two results are very close. The manufacturer solutions again keep just one solution per beam and fail to show the lifeboat davits. This problem is solved by the extra detection feature because the echo envelope is really clear to see, so we can feel the davits and then the seabed. Here my seabed, here the davits. That's why the extra detection is working pretty good here. And PDI seeing one time by time looks like represent very similar to the previous one, perhaps with a little more detail. Example number 6, the midsection with a loading spar. Kongsberg solutions focus on the highest depths and give us some points here, but it's hard to see what this means, what does it represent. The extra detection are able to define the upper ribs. I'm call this part here as ribs, so define the upper ribs and indicate the presence of the two loading spars. This part here. And then the PDI displays everything in reasonable details. Example number 7, the longitudinal profile of GB Church. Again, Kongsberg solution limited to one solution per beam. Extra detection can highlight the upper part of the mast and indicate the presence of some ribs above the main deck. And PDI can display the mast completely. Part of the loading spares, the ribs, and even submerged clouds. Just kidding, they are probably spikes. Example number 8, the last one, the rear mast of Mackenzie shipwreck. This is the case that I like the most because this is my first result ever, and it made me believe that this idea was not crazy, and motivated me to follow this path until today. That's why I asked Collins to put it on my flyer. As PDI allows more than one solution per time slice, all the details of the mast can be displayed here, and the solution from the PDI stands out from the other. You can see that the extra detection is doing a great job here on the top of the mast. Kongsberg just getting half of them, but the real detection of the mast just happening here. Well, the examples that I have shown kind of lead us to some conclusions, and I just highlight a few of them. The first one is using only time series is not always the best alternative. PDI can provide complementary solutions, mainly in the presence of mass-like objects. In situations that occur multiple detection within the same beam, or in situations where the shape of the object results in abrupt depth or a cross track distance variation between consecutive beams. There are still many things to improve in my work, and a few of them include calculations of the uncertainty of each sounding. I tried. My dream was to give Brian a number for each sounding, the uncertainty for each sounding, but some limitations of deadlines and the absence of some information in datagram did not let me to succeed in this aspect. Improvement of the automatic threshold, as can be seen, the automatic threshold still has imperfection, allowing spikes to occur. It has been minimized with the joint use of an initial threshold filter, but the initial one depends on a good choice of a reference value. The idea would be find a combination between the two that could be truly called automatic. Establishing a criteria for rejection of soundings using a long track filter. I did not mention this throughout the presentation, as each example includes only one ping, but the target displayed by the PDI are presented in more consecutive pings than in conventional match. So these points here are some cubes, as this one here, and we can see that I can see the cube before the conventional one, and I keep seeing them after. So this suggests that the transmission side lobes are used in my calculation. So I can detect the transmission side lobe, and it's not good. So a long track filtering would be nice for future works. Convince manufacturers and operators that logging water column data is beneficial. This data can be twice the size of amplitude data, and being able to store them can be challenging, but we can improve our results. And a combined use of all approach. It would be nice to use the best of them all to create an ideal bottom detection algorithm. Well, this is all I tried to highlight from my thesis. I'm leaving my email here in case of any questions after this meeting. And I hope it has been a pleasant time so far. Thank you all for your attention.
Thank you, Leo. The 41 attendees can't clap or they can't be heard, but I'm sure they're roaring away. What we normally do at this point is we have at least 2 rounds of questions from the committee first, and then we will open it up to the rest of the group. And I suggest, as I'm the supervisor, I should go last. So if Brian and Tom, one of you, Brian, your video's on first. Would you be prepared to go ahead with questions in the start?
Yeah, can do. Leo, thank you for that. That's a very good presentation. You mentioned it a little bit, but you mentioned a bit more in your thesis document. I want to talk about side lobes for a second. And one of the things that you talked about was trying to detect when you're seeing side lobes and to avoid having to use them, whether that's transmit side lobes along track or side lobes, receive side lobes cross track. I want to start with the receive side lobes. As part of your work, you tried to detect them, but you only did it really within a single beam, looking at them. And it seems to me that because they're often correlated, looking across multiple beams might be more productive because you'll be able to see them in multiple beams and therefore detect that they are in fact side lobes. Is that something you've considered? Do you think that could be worked into your algorithm?
I'm not sure I get the right question. I'm the king of misunderstanding questions, but I think you are asking me that if I did something to reject side lobes using time slice. Is that right?
Mm-hmm. Yep.
Yeah.
The question really, Leo, was about, in your thesis at least, what you said you were doing is you're just trying to do it within a beam, just looking for side lobes, trying to detect them at one point. But it occurs to me that, you know, if you think about the conventional wedge plot, side lobes often appear along one time ring, you know, because they're a strong reflection. Like the seafloor is the most common one. You see it, a nice little ring
Exactly.
that crosses a nadir. What I was suggesting is that if you could use multiple beams and look for correlations at the same timestamp, would tell you that this really was in fact a side lobe, because real things wouldn't show up like that. Could you build that into your algorithm?
Not sure. Let me just try to return one slide here. So here's one case. We have the first touch in the seabed, and this is all the side lobes.
Mm-hmm.
And looking in this presentation here, in this graphical representation, it's kind of easy. You can see that within one time slice, it's we can feel this. It's hard to see in a Cartesian way, but here you can see maybe a time slice 100 and something.
Mm-hmm.
I have small, not higher values, so low values and a high one. So the way I'm doing, just selecting the stronger one from one time slice, I'm kind of doing this. The way of picking the here. Okay. So imagine we have this time slice here. As I'm just considering the stronger one, I'm rejecting all these side lobes.
Mm-hmm.
And the problem I have is when I have different sectors. For example, I'm not sure it's easier to see for you, but I have 3 sectors here. It's interference sectors. And sometimes when I analyze just one sector here, I have no idea if the highest information from this sector is related to this one here. So normally I get spikes around here, because the way I'm doing, I'm just looking for each sector individually. Mm-hmm. And would be really nice to do something to prevent this. So my initial thought that I did not put in my code is using the information from the conventional time series to kind of give us an idea of where is the first touch, or when we have something like this, and avoid everything before then. But I still don't know how to make it work, because in some cases I can reject important data. So it's tricky. I'm not sure I answer you, but I know the problem, but I'm not sure how to solve this.
Okay, but there's nothing that would stop you from trying it. There's nothing fundamental about the algorithm that would prevent it from working. Okay, so let me follow on question then. Let's go in the other direction now and talk about the along track, the transmit side lobes. And you said right at the end in your conclusions that, you know, trying to work out how to remove them was something that you thought was future work to avoid targets being spread out over a much wider area. It occurs to me, though, that if you could use them, they actually might be beneficial, because what's happening is, if you imagine you have a target, you're seeing it beforehand, and then you're seeing it as you go across, and then you're seeing it behind as well. So you're actually getting multiple hits in the same target that confirms that it is in fact a target, if you can do the georeferencing. So my question is, do you think it's possible to do the georeferencing and use those rather than reject them to confirm that you do actually have targets?
Yes, I think it's possible to use. I tried, but my ray tracing algorithm is not perfect. I can just work in one beam, and if I could, I would show it here, but I didn't manage to complete this. But it would be nice to reference all the swaths, all the conceptual ones, and then it would be easy to identify what is really a side lobe or a main detection. And actually, there are former works, previous students that did it. They kind of apply a BDI approach in a long track direction, and it helped the study to identify what is the side lobe or what's the main lobe for detection. So it's easily feasible.
Okay.
After you can perform your ray tracing code with a better.
So a bit of development still needs to be done to make that work, but it is possible. Okay. All right, I'll pass the question.
Tom?
Tom, I think you're next.
Okay, hang on, sorry. I've lost my ability to turn my video. Oh, no, I haven't. Okay. Thank you. And Leo, thank you for the presentation and for the thesis itself. I found it to be really well done, and I thought that your presentation was excellent, and I thought that your writing was really good. I feel like I'm gushing here, but I really felt like this was a nice creative piece of work that you've done, and I enjoyed thinking about some of the same things that you were writing about. So thank you for that. I think there's a lot of, I like how you looked at this data, and I think it brings out a lot of the underlying information that maybe is there in the multibeam data that we have not fully exploited. And that came through loud and clear. And so I really appreciated that and had fun thinking about it. I have a general question for you, and that is that the underlying data is the underlying data, no matter which way you process the data, whether you want to look at a time slice or whether you would like to look at a constant angle slice, the underlying data and all of its uncertainties and the physics behind it, the data are just the data. And so can you comment on that and what you think about that in terms of what the advantage of looking at it at a constant time slice is versus looking at a constant? I know this is underlying your data, underlying a lot of what you said, and you showed some comparisons between your approach and the sort of internal inside the Black Kongsberg EM box result, but with neglecting what goes on inside that black box, can you talk about, like, inherently what is the difference? Should it, I guess my question is, should it end up all at the same place no matter which way you look at the data, or is there something inherently better about the PDI approach that you think?
I think I have a figure that could help me. Just a moment. Let me try this one here. I'm presenting here, let me turn on my laser point. I'm presenting here one swath, and it's related with the 1 meter cubed. With one of them that the Congress solution give us a gap here, and this feature here should be the cube. So we don't have them in the phase information, but they have rejected data that can kind of represent something for us. So what I did was take a bunch of time series, a bunch of angle slices to try to see what's happening. And if we look for the phase information, we have the amplitude one here, it's a sequential, being number 239 up to 244. And if you look at the phase information, we can see the phase ramp and something here, and the phase ramp goes away. So in many of them, there is not a clear phase ramp. You have some interference here, and it's exactly the cube. So I tried to create a 3D plot of this. This is just a random information, and the perfect phase ramp came from here, but we can see the interference here. So it's, in this case, it's hard to have a phase detection because when you try to fit a low polynomial order in this data, we kind of have a bad variance of information, not fit very well. But then when we look for this information using a time slice, look how nice and clear is this time slice. So there are some situations that it's better to use time slice as a, I think that's the point of my presentation. When there is not a favorable one, when we can use both of them, it is preferred to use the time series, because when we are just using time series, we have a bunch of procedures, and we perform a moving average. We do a bunch of statistics to get the best and more accurate solutions. So the way I could answer is, the solution number one, the preferable way to do this is using time series, as we have done for 30 years or more. But we should try also time slice and check them. When they match, it's okay. When they do not match, we kind of may put this as an extra layer, or at some point for the operator check after. So just give it as we do in the extra detection. Just have the main information plus the extra one, and you can use or not the extra. We could try this with time slice. Create a layer with extra detection from time slice and let the operator choose which one is better. I think this could be the future, at least what I think it's good to do. Not sure I answer.
No, I think you're getting at something really interesting with that. And I guess I'm happy that you went there, because that sort of leads me into my next question. I guess first to comment on that, and that is that when I look at those phase ramps that you have on the screen right now, I see a lot of coherence in those phase ramps associated with that object on the seabed, and I think that's real. And I think, no, you should not try to fit a single line all the way through that phase ramp. I think that would not be, that would probably not be what you would want to do. You would want to use a smaller section of the phase ramp in order to fit that line through there. And then you probably wouldn't be smoothing through the object on the seabed. That would be my first thought looking at that data. And then can you go to the next slide that you were just showing, which had your approach with some of the PDI data, the slice through the other view there. Yeah. And so you have two things on there. You've got the amplitude data, and then you've got that slice that goes nicely through you've got the phase ramp, or the PDI ramp, I guess the ramp in angle space there. And one of the things that I was thinking about in your thesis, you have a different plot in your thesis but I really liked it. It's similar information to what you have here, and it had one of the phase ramps in time series, and then it had one that looked just like this on the upper right for your time slice. And I was just noting that the phase ramp from the PDI data looked an awful lot cleaner than it did in the time slice. And I'm wondering about that and why you think that is. What is driving the uncertainty in both of those? And I guess underlying that is my initial comment that I made, which is underlying all of this, the data are the data are the data, and you're just slicing it in two different ways, and the physics are still the physics. So what makes this look so much cleaner than the time slice? Why it looks remarkably smooth? What's behind that?
Let's return to this one here. Each point here represents a different time sample. So it's saving and save again, just registering everything. And I believe that the noise information is different for each point. So in the initial one, we have one noise, and the next one, a different noise. But when I do a time slice, consider that I don't have a directional noise. It's coming omnidirectional way. I believe that all the data receive the same input as noise, so they all goes up or down together, not changing that much the way that they are in this compared to each other. I mean, so if I had a phase hamper and I insert noise in the same time slice, they just go up and down differently in the time series, because each time has a different error, so a different noise. Sorry. So that's why I have this strange representation, this same graphical way. And it's also presenting the amplitude one. And one of the reasons that we do moving average to move the curve. So that's my point. All the noise comes together for the transducer and affect all the data. The relative information of them is preserved.
I think I agree with you. I think that in the time series, it's the individual points are independent because the pulse is interacting with a different piece of the seabed. And the figure that you had up when you were answering Brian's question kind of showed a nice cartoon of that, where you had the cartoon seabed and then the pulse at this one right here. So at an instant in time, I'm looking at the left-hand cartoon, it's the red dashed line, and I'm going to ignore the fact that it's intersecting with the seabed twice. Let's assume the seabed's more smooth than that. So the response at that instant in time is only coming from where that star is. And at an earlier time or a later time, the pulse is actually interacting with a different piece of the seabed. And hope, sometimes this is true and sometimes maybe it's not true, but if what is driving the uncertainty in the phase ramp is baseline decorrelation, which has to do with how much, if you think about the two gray-black dashed lines that describe your beam, baseline decorrelation basically says how wide is the intersection of the pulse with the seafloor compared to the width of that beam. The wider it is, the noisier it is. But the important point is that it's actually, we see a different random noise for every time step along there. That's in the time series. When you look at the PDI, you actually only, all of the data, the uncertainty is actually, I think, exactly the same. I don't think that there's any more or less noise in the data. It's just that if what's driving this, and let's just assume it's baseline decorrelation, if that's what's driving it, there is only every one of those beams that are adjacent sees the exact same spot on the seabed. And that suggests to me that in the time series, the data, that noise is representing independent data. And in the PDI, when you look at all those beams, that's the same bit of the seafloor just coming back in with some different beamforming algorithm, and the data aren't actually independent. That doesn't mean that it's not a useful way to go and get a zero crossing. But I think that when you do get to the level of trying to quantify the uncertainty in both approaches, which I think is really important to do in order to compare them properly, I think that one of the things you have to be careful about is whether or not each one of those adjacent beams is actually an independent observation of the seabed in terms of the uncertainty quantification. I'm not sure that I don't think I've pulled I'm not sure I completely understand all the ins and outs there. I just think it's something to consider. But I love that what you've done has made it even possible to ask those questions and to think about this. So again, nice job, and I will leave it there.
Means a lot to me.
Okay, I'll go third. Just obviously I've heard this story and listening to the other questions, obviously many of the things I'd love to ask are gone now. But one of the points that came up, and I can't remember if it was you or one of the committee mentioned, is let the operator choose. And what's become scary from a data management point of view, you have to store all this data in a ping. And for those not aware, one of the things Leo did was really remarkable. This is one of the first people to handle KML. He wrote a completely independent native reader. And it seems very simple when you store everything beam by beam by beam. Konsberg already broke it by adding high definition, so there are multiple solutions in a beam. And now if we were to go with your PDI approach, you can no longer sort it by beam. You'd have to write a telegram that either gave angles for every time slice or just a random two-dimensional array. Have you thought, if people start bringing back BDI and PDI, have you got any pie in the sky ways that they're going to be able to write a data telegram that would store, as you point out in your thesis, you point out that, you know, there's a couple of thousand time slices that might have answers. How do you, have you got any thoughts about how you would actually store this mess?
Yeah, actually, no, I didn't thought about this. I just believe you can put more hard disk inside the computer, but I don't think that the solutions from PDI or any other is actually a problem. I mean, it's hard to store the water column data. It's hard to store the amplitude and phase from water column, but the solution would not be that much large. So they could do this in real time and save the solution for us. And it's up to the operator, save or not the water column data. But the solution will be there. We just need to load and show, okay, it's good. Let me reject, let me consider this one. So solutions for PDI would not be a problem. What is actually a problem is what we already have. How to save this amplitude and phase water column data.
Okay. And you mentioned your frustration in, because Brian didn't ask it, the uncertainty. So I know you've thought about it. As Tom mentioned, one time slice, they're not independent. So did you have some thoughts, even though you chose not to address it in detail in your thesis? What extra would you have to do in order to start giving someone an idea of angular or temporal uncertainty for one of your solutions?
Yes, John, let me bring you another reading the slides. Let me check this one. It's not the best one, a bunch of words, but the points here, okay, not this one. In 2000, Javier Lurton had made an article talking about how to use a quality factor, and they call it as Framer quality factor, and it's able to measure the uncertainty for each sounding. So I tried to use this. It's defined as this way here, the logarithm of the depth over the uncertainty of the depth. And he basically divided in two cases. The first one is when we are looking for time, we are looking in time series, you could change this and have all the conclusions. And the second way he do is looking on time slice, because it's relevant for interferometric side-scan sonar. It's the same principle, they use just one time slice per time. So my initial idea was, let me try to calculate uncertainty using the same way using interferometric side-scan. But the way that article and a bunch of other approach this lead us to information, which is the signal to noise ratio. So this was my problem. The way I'm working with my data, I'm just getting the highest information and rejecting everything. So I actually don't have information about what's my signal, what's my noise. So I could not manage how to solve this uncertainty in the difference of phase measurement. If I could solve this, I could just follow the path that Javier Luton made and reach a number. And other solutions that don't need signal to noise ratio use time averaging. So they grab a bunch of sequential pings, make a time average, and it helps us to get rid of this signal to noise ratio. But in the way I was trying to do with PDI was just checking one time by time, not do time average, because I'd like to see the best resolution I could. So that's I didn't reach any point. But I really do believe that the way to approach the uncertainty calculation would be following the path from this article made by Javier Luton.
I think just a last comment, you mentioned the sector boundaries. You've gone into great detail in your thesis about that. You responded to Brian saying, if it's a side lobe from a main lobe outside the sector, you don't know about it. I know you haven't done it, but if you were to apply this to a system with many more sectors, like the deeper water systems or the Atlas systems, is it going to be harder when your sectors get smaller? If you have, in other words, more sectors, but less beams in a single sector?
I'm lucky today because I have a bunch of figures here that could happen. Here is just to everyone understand what is happening. So I have one sector here, and all my automatic threshold is applied in this blue sector. So that's all perfect, and I get this the solution from here and from here, which represent these 2 points. The problem is, in other sector, I should reject everything, but I have one peak that is stronger than the other. Even it's not as strong as the blue sector, but in terms of red sector, it's stand out. So my automatic threshold grab this point here and create a spike for me. So this is one of my problems. When I try to get just these 2 points, I end up getting 3 points. So I spike here. I kind of minimized it using my initial threshold. So if I could reject everything below here, below 0, for example, in this graph here, I would reject this one. So this one would be nice. And you are right, using more sector would be a problem. But luckily, I had the opportunity to try it with EM 124, which has 80 sectors. And it's not the best representation. What I'm showing you is my MATLAB coding, the window that I use to work on my project. So you can see here 8 different sectors, and the solutions still exist. I still have the PI is still working even with 8 sectors. I can see on spike here, but looks like there are a combination between my automatic and initial threshold can solve the problem. So, the answer is I just need a better automatic threshold, and the problem with the sector will be gone.
Okay. Well, thank you. I'll just check whether Brian and Tom, do you want to do any more questions? Or
I have lots more questions. Like Tom, I enjoyed thinking about this and reading the thesis too, but I think we better give the audience a bit of a chance before we move any further.
Okay, I'm not terribly skilled. I can see there's 31 attendees. I'm not sure how to make them available. If anybody wants to ask the question, see if you can raise a hand.
So a couple of different ways you can do it. You can put a question in the Q&A and we'll see it. Or if you want to raise your hand, we'll see that too, and we can get you promoted so you can actually talk yourself if you want to. Okay. I think everybody's shy.
Yeah, it's all over the planet, actually, when you look at the people. It's remarkable. Appreciate people coming in different time zones.
One of the benefits of everybody being at home, I guess.
Yeah. Well, if anyone, I'll keep an eye for hand raised. But in the meantime, Brian, Tom, do you want to ask anything more?
Yeah, I'll go for another question. I think you mentioned it a little bit in your response to Tom, but the question I wanted to ask next was about combining your method with conventional methods or traditional methods or whatever you want to do. And you mentioned in your thesis that you saw a model where you would turn on doing the PDI computation if it looked like the conventional methods were not working. I don't have any problem with that. I like the idea of a try harder mode. I've done it myself in different contexts. But what I was interested in is what you thought was going to trigger that decision. So if I look at one of the conventional approaches, if I run like a pair beam time series analysis with amplitude and phase detects, what do you think I should be looking for to convince me that it's not doing the right thing and I should turn on the alternative processing? What would be the logic there that you want to use?
I think the answer is something that I don't have. That is the uncertainty measurement. If I could provide this ephremic quality factor, I would have a number for each sounding, and we could use a reference value of this ephremic quality factor as a threshold, a filter. So everything that is greater than 3, I'm not sure how huge is the number, but everything that is greater than my reference should be accepted or is a great candidate to be accepted, and smaller than that would be ignored. It could be just a spike.
So the idea would be that you run the conventional algorithm, and if the quality factor doesn't quite get to the right level, then you run the auxiliary algorithm as well.
Actually, I think you should run they both. We have all the solutions.
That's what then use the.
Yeah, I think every time we should do everything. It's hard, a lot of things to do, but using time series and time slice, you would end up with a bunch of solutions, maybe 1,000 of them, and we could use this something similar to the ephremic quality factor to select the best ones or just highlight for the operator. This range of soundings, this soundings here are good, this one I'm not sure, this other here are trash, and we could kind of select the one that we believe is true.
Okay. I was about to say exactly the same thing. Is I don't see any reason why you wouldn't run all of the algorithms and then try and work it out. But that seemed to be what you were suggesting. So I'm glad to see that wasn't your intent. I can see there being issues with trying to understand when to accept, which solutions to accept, because you don't have the same requirement as you do in a pair beam time series where you have one answer. Because you can have multiple answers if you're looking across the beams. It might be interesting to look at that. What do you think is, one of the reasons why you might not want to do that is just computational cost of doing the extra algorithm, because it's already, if you look at the beamformers and bottom detection algorithms in these systems, they're already using a fairly extreme, multiple parallel solution to try and get to fast enough processing rates, particularly for shallow water. So what do you think is the computational complexity of your algorithm? How much extra processing do you think you'd be adding if you asked the manufacturers to run this? What's your ask of the manufacturers in terms of how much extra compute power they have to commit to their system, recognizing that extra compute power is extra cost?
My skills in programming is not the best one, so my initial tries was really bad. So I just tried to run a couple of solutions, and it took me, the worst case took me 12 hours. It's just a problem with my code. After some time, I could manage to make it better, and now it's just 1 second, and I have everything. Much more than a second, much less than a second. So I really do not believe that computational processing time would be a problem. The speed that you use and the way they do all the information, they already have everything. They just need to change some just increase a function and get the results. It's really fast, and I'm using the MATLAB, which is not the fastest one you can use. Using other different programming languages that they use in the sonar system. I really do believe they can perform this in real time, and the operator will not feel the difference. It's just saving, maybe the speed of storage could be changed. For a regular operator, it's just start and stop, and nothing else would be changed.
So it sounds like they're already doing the heavy lifting that's required by making the data available for the other methods. So there's not much extra to be added for your method, is what you're saying.
Is that they have everything they need to change from time series to time slice. All the information is there. Just a function to tell the computer what to do, and they're going to have everything.
Yeah. Okay.
Everything that I have done came from the information that I already had. I did not insert anything new. I'm just using the same data and applying a function, and it's really fast. They have the data. The data is loaded in the computer because they are showing us all these water column information, seabed, waterfall. They have a bunch of representations. So this data is already loaded in the memory. They just need to perform a function and save these results.
All right. Good. It's always good to hear, particularly when we have a number of the manufacturers on the line with us as well. I'm sure they'll be happy to hear it. I'm happy to pass the questioning, Tom, if you want to have another question you'd like to ask.
Sure. You showed Xavier's paper, I think, with his quality factor. And I think that you were thinking that you were going to use the one that had the angular uncertainty in there. And I guess my first question is when you get that, is that, how would you, have you thought about how you would implement that? Would it be a data-driven thing or a physics-driven thing, or how does Xavier intend for that to happen? Does that come from looking at residuals or what?
I'm not sure again. You mean what to do with the infrared quality factor, or how to get the infrared quality factor? I don't get the question, sorry.
How would you get that quality factor from your data?
The answer is I don't know. That's why I failed in having answered one.
Okay.
But the approach they use in the interferometric side-scan sonar is this one here, and they create the quality factor just checking the steering angle and the uncertainty related to this steering angle. Let's do. I mess up. This is the correct thing. And knowing this information here, which I don't know, they get a number that is the quality factor and apply here, and this is just a number. My quality factor is 11, is 8, so it's the greater is better and the lower is worse. So I try to follow all the path from this uncertainty angle, and I put it on my thesis. I convert this angle up to the information of the difference of phase, and I try to get an uncertainty related to the difference of phase, and that's where I end up, because it's leads us to an expression. They two here are just constant numbers, but this D is my real problem. I don't know the signal to noise ratio. What is tricky for me is that we have in the datagram information from quality factor saved. So the echo sounder system is able to perform these calculations. Somehow they know the signal to noise ratio, they know information, but it's not clear saved to us. So I really do believe that manufacturers that already saved this quality factor information for his one data could just adjust this for the interferometric case and show us a result. In my thesis, I just put the idea that would be a path, but I could not convert this in numbers. I do believe manufacturers can do that.
I think that when you look at the uncertainty in a split aperture correlator, it can be related to the signal to noise ratio, but that's not the only limiting factor. I think if you go back and look at Jin and Tang's work, which you also reference, there are other effects there that are not just the normal signal to noise ratio that we think about when we think about sonar data. That's an aside though. If my guess is that, and I don't know because I'm not the manufacturer, but my guess is that when you look at equation 3, you have a good idea of what theta is, and the idea is to estimate that delta theta. And so you could imagine that if you are a phase differencing bathymetric side scan, then you have that phase ramp and you can fit a line and look at the residuals, and you could come up with some estimate. Whether that's how they do it or not, I don't know, but you could imagine looking at the residuals to come up with an empirical assessment of that delta theta, which is what you need in order to measure, in order to actually go and calculate what equation 3 is. My question to you is, where would those residuals come from in your approach? What would you be taking the residual of? Like, how would you go? It's not really a fair question. If you haven't thought down this path, that's okay. You could just say, I don't know. I'm just wondering if you have thought about that and you were going to go look at the residuals, which I think maybe is one of the approaches to doing that quality factor. Residuals of what?
I think the fair answer is I don't know.
Fair enough.
But I try to read some papers to understand how they are managed to calculate something similar to a frame quality factor for these time slice for interferometric side scan sonars, and looks like they are relating what they call signal and compare with all the other data, and they call this as noise. So if I'm just using this point here, this would be my signal, and an average or something like that of this data here would be my noise. And they compare they both to try to get a signal to noise ratio, something like that. But I didn't was able to get any further or to understand better to really make it work for me.
Okay. I don't think that will work, that approach. But also fair enough. I think it would be, it would be interesting to chat about that offline. I think I think that's not probably the way to do it, but the actual way to do it is also not obvious, because I think that there is a problem with a lack of data independence along a constant time slice. And I think it makes it non-trivial to come up with that uncertainty number unless you look across multiple time samples. And maybe that's not fair to your approach, I don't know. So it'd be interesting to chat further about that, but at a different time. Thanks, Leo. I think I have no further questions, John.
Okay, and I'll just have one thought which hadn't occurred to me till I was listening to you just talk to Brian, and the conclusion was the heavy lifting has been done by the manufacturer and that they have all the information, and actually they have a lot more than they left you with in the end, because in your thesis one of the concerns you had is as you tried to do your threshold on a time slice by time slice, to save data volume, and we all appreciate that, they've cut out the echo after the what they think is the bottom detection. But of course they have that in real time. And also I think they have the data we get in water column and phase, I think is subsampled by at least a factor of 2, if not 4. So it only sort of occurred to me as you were discussing with Brian, but potentially the best place to be looking at this algorithm is when you have all the information. Do you just want to comment a little bit on, I mean, one of your conclusions, which is I was a little nervous of, was that you said, I wish they kept everything in the pie, and they don't.
I get you. In trouble because I'm all the time trying to take your face from my presentation. I'm sure you cannot see, but it's hard for me. Just to share with the people who didn't read my thesis so far. Here's the data, one example of the data we have, and what manufacturers do is, as they just use time series, after found the bottom, they stop recording or stop recording for us because they have all the data. Stop registering the data. So here it's around the nadir, they have the bottom and stop. Here it's go further because it's usually it's not range. But the result is when they take this image and put the complete swath, what we have is a huge part of the data is deleted. It's just erased. So if I need to perform a calculation in a time slice, as this one that I'm trying to draw, I would have nothing from here up to here, and just a small piece of information for this time slice. So using the time slice with erased data is tricky. It leads me to try a bunch of other solutions. But if I have everything, my statistics would be performing in a better way. Yeah, this is the example here. Draw, and I just have one peak here. So is it good enough? Should I reject this one? Should I accept? I have not enough information to think about just one amplitude peak. Although I have a zero cross phasing, I'm not sure if I should reject or accept this one. So the gaps is really a problem, and they have this information, so it's really easy for them to generate these solutions. The one who's having problem is me because I have less information.
Okay, without them giving you that 65% of data and all of us gagging on the sheer data volume, could they give you statistics of the missing information, maybe, do you think, that would give you enough so that you can decide if that one peak on the right is left? What would they have to keep? Do they have to give you all the other information, or just some significant statistics?
Yeah, you are right. The way I'm performing my automatic threshold, I just need to know what is the maximum, minimum, not a bunch, maybe 6 variables. So if they could save just this information, the maximum peak is negative 20 dB, the minimum peak is 10. So give me the information, I would be able to perform this automatic threshold, even not having the data, and actually don't need this data for nothing else because it's kind of below the seabed. But in my case now, I need for the statistics, if they give me the numbers that I need, they can just keep doing this and erasing everything. The water column is smaller, which is huge. Even the smaller one is huge.
Yeah, well, and again, just like Tom, I think we'd love to talk about this more offline, but that's all the questions I have. Thank you very much. And just looking at attendees, no raising hands before we go into a committee discussion. Any last chance for people to ask anything? Going once.
Yep.
Going twice. Okay, I'm not quite sure, Brian, this is my first Zoom defense in control, if anyone's in control. Do we just drop down to 3 of us somehow at this point?
Yeah, what we're going to do is, unless you want to start another Zoom meeting, we should just ask everybody, or well, first thing we should do is to thank Leo for his presentation and thank everybody for being here. But then ask all of the participants, the attendees, please to leave the meeting now so that we can go into committee session.